So welcome everyone. It's very exciting, at least for me today, that we can continue our workshop today. Yesterday we have several very exciting talks about social media, like misinformation, etc. And as we can see currently, the trustworthy machine learning, including security, privacy, fairness, like generalization, and all the different aspects are quite important and like investigated by both industry and academia domains. So today we will continue our workshop, and we have quite excited speakers from Zhang from ETH and Rico Cotter from CMU and Mandre and other people will introduce later in detail. So okay, with that, we will welcome our first speaker, Professor Zhang from ETH. So let me have a quick introduction for Professor Zhang, who is an old friend, and we have discussed a lot about robustness and security, privacy, and I always inspired by a lot of exciting ideas from the machine learning platform perspective from Professor Zhang. So more concretely, Professor Zhang is an assistant professor in the computer science at ETH Zurich, and he's a great researcher on the next generation of machine learning platform. And he believes that very interesting, like by making data along with the processing of data easily accessible to non-expert users, we will make the makes the world a better place, which is quite exciting. And his current research focuses on building data systems to support machine learning and help facilitate other science, such as chemistry, like physics, and a lot of even like help protecting environment by planting more trees. Right? I think those are very exciting topics. And before joining ETH, so he's advised by Chris Ray from Stanford. And his research has contributed to several like great awards, including the SIGMOD Best Paper Award, SIGMOD Research Highlight Award, and his research has, of course, been featured by many special issues, including the Science Magazine, Communications of ACM, Best VLDB, Nature Science, etc. And okay, so welcome, and we're excited to get your talk started.
Yeah, thanks for the introduction. Everyone, thanks for coming to my talk today. I'm really excited to share with you some of our latest progress about essentially try to understand data for end-to-end machine learning applications. So I think everyone here really witnessed the rapid progress of machine learning system and platform over the last decades, right? So essentially, if you look at the landscape, pretty much every single machine learning kind of like cloud service providers now have their machine learning platforms. And also there's a whole diverse range of academic prototypes to really advance different aspects of machine learning platforms. So because of these efforts, so training a machine learning model has become really much faster if you compare that with like 10 years ago. And also on the other hand, the training process itself has also become more automatic and more systematic. So given all of this progress, I think it's fair to say today that for a user of machine learning platforms, getting some machine learning models has never been easier. For most of those users, they can just drag and drop their data set into a machine learning platform and get a model out. So, but if you think about whether they are actually getting the right machine learning model, we are going to talk about what the right really means. It's actually a very different story. So from our experience, really thinking about machine learning systems, we see two trends. So of course, this is very biased personal view, but there are actually two interesting trends that we see nowadays. So the first trend is that because building machine learning applications have become so much easier compared with 10 years ago. So those people who are building machine learning applications are actually start to shift from machine learning and computer science expert who really understand what the system is trying to do to really domain expert who have a really deep understanding and deeply care about their own applications in their domain, however, might not really that familiar with machine learning and computer science. This is actually one trend that we see, at least in many of our kind of experience. So because machine learning have become so impactful to our society, they start to have regulations like around machine learning applications, but also there start to have requirements that goes beyond just getting a good accuracy, right? So there's the GDPR and also the European Union's regulation on AI, right? So there's a whole bunch of requirement on robustness, reliability, so on and so forth. So given this trend, we kind of see essentially two consequences of these two trends. The first one is that you think about the user who are building machine learning application today, it's actually become less about training a single machine learning model or serving a single machine learning model, but more about try to understand the model, try to understand the data, how to expand the model, how to verify the property of both data and the model, how to monitor the model behavior, how to conduct testing, how to guarantee compliance with regulations. So, and the second consequence is because people who are building those machine applications are shifting to more and more to domain experts, right? So it's actually building machine application that actually that is compliant to those regulations and satisfy those requirements sometimes become actually more difficult for domain expert to handle. So essentially, we are talking about essentially one technical gap between essentially two different aspects. The first one is if we want to unleash the potential of machine learning to everyone, to make sure everyone who can benefit from machine learning application is able to build one, we have to deal with users who actually know less about machine learning and computer science, but more about their specific domain. So, but on the other hand, because of all those new requirements and regulations, we need to deal with a whole bunch of technical complexities. So today we actually see this gap become actually larger and larger. And the question that our group are very interested in is actually how to close this gap. And our view on this, of course, very best view, is that we kind of need to close this gap via a system approach to really accommodate the trade-off between democratization of machine learning to users who are not that experienced, and also to the technical complexity that we need to really be compliant to those regulations. So this is a question that I actually have no idea how to answer. So in this talk, I'm going to talk about something that we have been working on actually toward understanding that grand question. That is, how can we enable the development of machine learning applications from a more model-centric view to a more data-centric view. So specifically, we try to understand how can we provide system support for users to understand the impact of data to machine learning models. The reason we are curious about this question is, as we will see, a better understanding of the data can sometimes help you to get a better machine learning model. And better sometimes means better accuracy, better robustness, or better fairness. Now, we want to make this process of understanding data as systematic as possible to our users. So again, this is still another question that I have no idea how to answer. So in this talk, I've actually focused on some things that I actually know how to talk about. That is, I will focus on two specific examples of what do I mean by understanding. So here's our setting. So assuming you have a data set, this is your training set, and sometimes the data is not perfect, right? So there could be missing values and there could be noise in your training set. And then people build a machine learning pipeline over that. An end-to-end machine learning pipeline contains a feature extractor, take as input this training set and conduct some data transformation to produce another data set, followed by a machine learning training process, which output a machine learning model. And you can measure different properties of this model. For example, you have the accuracy or fairness or robustness metrics of this basic model. So we focus on two different questions. The first question is, given this end-to-end machine learning pipeline, so because there are so many data problems in my input, which data problem is the most important one to my final machine learning utility? If there's some data problem that I can fix, for example, I can clean some of the cell, which cell should I clean first in order to get better accuracy or fairness or robustness? And the second question is actually, which training example is most important for my final machine learning utility? Right? If I can remove some of the input data examples, which one should I remove to make sure I can increase my utility as fast as possible? So these are actually two questions that I want to talk about today. So here's how we think about this. We think there's one way to think about it, the right way to think about it. So for the first question, about the impact of the noise in the data to the final machine learning utility, we're actually curious about computing the entropy or the expectation of the final machine learning utility over the input noise. And second, to really understand the influence of each data example, we're kind of curious about how to compute the Shapley value or expected marginal improvement of the final machine learning utility. So there are 4 things that we know. The first one is not surprising, right? So if you give me a generic machine learning pipeline, computing these fundamental quantities are really hard for real-world machine learning pipelines. However, surprisingly, actually, right to us in the beginning, is actually there exists a family of simpler machine learning pipelines for which you can actually compute these 2 quantities in p time. So, and the second is once you have those simpler family of pipelines, you can actually use them as a proxy to reason about those more complex pipelines. And once you have those proxy, you actually can provide understanding of the data to the user. And once you provide those understanding to the user, it can actually help them to improve the model utility more easily. So this is the 4th thing that we have been learning over the last couple of years. And I will share with you essentially what we know today. So in this talk, I will talk about 2 things. The first one, I will spend some time to tell you what we know on the theoretical side. How do we think about the impact of data noise to machine learning training? How can we think about data importance to machine learning training? And how can we kind of approximate a real-world machine learning pipeline using a simpler pipeline that can compute entropy and Shapley value in p time? And then, given those, we will show you essentially how to do a whole bunch of machine learning tasks. For example, data debugging, data cleaning, or building a data market, right? So using this theoretical result. So now let's talk about theory a little bit. So the first question that we kind of want to understand is you have a training side, and then there could be missing value, there could be noise on data. Anyway, there's uncertainty on features in your training side. And then you train a machine learning model over that. You measure some metrics of this trained model. Essentially, we want to understand what is the impact of all those uncertainties of input training data to the final machine learning accuracy, because not all of those uncertainty actually matters to your final utility. Before we try to understand this question, let's try to think about one thing. That is, when we talk about conduct training on this input data side with uncertainty or with missing value, what do we even mean by that? Because at least to us in the beginning, this is actually not that clear. So I'm a database guy. So when we think about this question, I often just go back to database to see what people are doing over the last half a century on this. Right? So essentially, before we talk about machine learning, if you use a database system and you ask a SQL query over some tables, some relations, there's also a similar notion of unknown or incomplete information in a database system. And people actually have been working on how to answer database queries over unknowns and incomplete information. So this actually goes to a notion called Null, which kind of confuses many undergraduate students in my database courses, but it's actually pretty simple. That is, assuming I have a relation with uncertainty. For example, for Kevin, I don't know the age, so I put a special state called Null there. And then if you are doing some data processing over this relation, for example, you try to find out the person with age smaller than 30, what would you have? In this case, you will never output Kevin, right? Because there's a special rule saying that if you compare Null with 30, right, the answer is I don't know, right? So one thing that actually we were trying to think about in the beginning is how to apply the similar semantics like to machine learning, and whether that can actually help us to understand the impact of noise to machine learning training. So to really answer that, right? So let's go a little bit deeper into essentially what is semantic of Null in database systems. So it's actually pretty interesting, and that actually goes to a concept called the sure answer or certain answer in database theory. So essentially, if you have a table look like this with certain uncertainty in it, and you try to ask a SQL query over this relation, what database system trying to do under the cover consider all the possible ways that you can fill in this incomplete information. In this case, right, so there's actually so many different ways to fill in this missing value. And for each of those possible worlds, you are going to ask the same query. For each possible world, get an answer. And what database is trying to do is only give you the answer that is that appears in all the possible worlds, no matter how you fill in this missing value. And that's called the short answer in database. So if you think about this, at least from the context of database, right? So it tries to enforce certain notion of robustness against uncertainty. It tries to give you an answer that's going to be there no matter how you fill in that uncertainty. If you think about this, actually there's nothing stop you from actually applying the same semantics to machine learning training. And that's actually something that we have been doing. So essentially, if you give me a relation with certain uncertainty in it, right, and you say, okay, let's train a machine learning model and make some prediction on some tuples. So what we have been trying to do is we take the same semantic. We consider so many different ways to fill in those missing values. And for each of the possible world, you train a machine learning model, you make a prediction, and then you try to aggregate them, right? If you think about the binary classification problem, if all of them give the same answer, you return the same answer. If they disagree, well, you can return null. Of course, you can have the softer way to aggregate them. You can compute the expectation or you compute the entropy. So essentially, this is what we have. You have input relation with some noise model, right? Essentially defines a probability distribution on many possible worlds. And we define the expect prediction on certain tuple as the following, that is, you train a single machine learning model. For each of the possible world, you make some prediction and you aggregate them. You can have the expectation, you can have the entropy, right? So if you think about why the entropy is interesting, is assuming the entropy goes to 0, right? It actually means that none of the noise or the uncertainty in your input training set matters for your final utility, right? So, and if you are considering data cleaning, right, it actually means that you don't need to clean anymore as long as your entropy is 0. So what are the challenges, right? So challenges here is actually, if you consider all of those possible worlds, as you can imagine, that could be pretty slow, right? If you have N rows and D columns, every single cell have 2 possibilities, right? We are talking about exponential many possible worlds that we need to train machine learning model on. So here's what we know. So for general classifiers, there's probably nothing else you can do, right? It's very hard, but you can still approximate using MCMC. But surprisingly, if you take a simpler classifier, for example, consider k-nearest neighbor classifier, what surprised us at the beginning is actually you can have a linear time algorithm to explore this exponential many possible world. So that's actually some result that's actually get us really surprised in the beginning. I won't go into the detail, so you have to trust me at this moment. So this is actually what we know about how to quantify the impact of data noise, of data and incompleteness to the final machine learning utility. So the second thing that we have been thinking about is about data importance. So essentially you have a training set, and then you have an end-to-end machine learning pipeline, start from feature extractor to machine learning training and to machine learning model, right? You try to understand what's the importance of each training example to the final machine learning accuracy or fairness, because not all of those input example matters for you. So to really think about this is how we think about this at this moment, that we try to the expected marginal improvement for each of these data examples. So let's say you have a training set with 4 different examples, and you try to say, okay, what's the importance of the right tuple, right? So you could really compute the utility of the whole data set, and then you remove the red tuple, then you get essentially improvement by adding this red tuple. That's already tell you something about how important this red tuple is. And you can actually do more. You can consider all the possible ways that you arrange the rest of the tuples, and then you compute essentially different type of improvement of the red tuple. You can actually aggregate them in some way as your answer. If you aggregate them in a certain way, it gives you the Shapley value. So which is a concept that has a very sound game theoretical foundation, has really many properties. People have been kind of showing it actually work well for data debugging for many applications. So, but what are the challenges here, right? So the challenge, again, is very similar to the first example. That is, if you want to consider all the possible ways to arrange all the other examples to compute the Shapley value, right? We are actually talking about exponential many possible worlds. For each, you need to actually train a machine learning model, right? So, and here's what we know. So for general classifiers, it's actually very hard to do. However, if you allow me to use essentially a simpler classifier, depending on what type of feature extraction pipeline that you have, you could have very efficient p-time algorithms to compute exactly the Shapley value for the final machine learning utility. So this is actually another thing that we know on the theory side. So putting these two side by side, right? So you can actually start to use them to actually approximate a real-world machine learning pipeline. So essentially, our current approach is we approximate a given kind of input data set into a cost table where every single cell have kind of different uncertainty, and then we approximate the feature extraction pipeline into something with kind of simpler structure, approximate the machine learning training process into a simpler classifier, the k-nearest neighbor classifier. And then we try to use this proxy pipeline to compute the entropy, compute the Shapley value, and use it to for the purpose of data debugging for the original data pipeline. So this is actually give you something that's actually quite useful. And let me actually show you a couple examples of how to use to do something useful. The first example that we have exploring is actually about data debugging. So here's a setting. Assume you have a training set with many kind of input training examples, and some of them could have, for example, a wrong label, right? And then you pipe this training set into a machine learning pipeline, right? And for example, your final utility is accuracy. So the question that we are curious about is how can we find out those training examples with wrong labels, right? So here, one idea is that if you think about the Shapley value of each of the training examples, so we would expect those with incorrect labels should have a kind of a small, often negative Shapley value. So in this case, for many of the machine learning pipelines, you can actually approximate them into something simpler and compute the Shapley value in an exact way, which give you something really much faster than doing MCMC over the original data set. And this actually give you a pretty powerful way for you to inspect those examples with the wrong label. Essentially, you could start from all the data examples, starting from the one with smallest Shapley value, and you try to identify whether they have the right label or not. If they have the wrong label, you give them the right label, right? So this actually give you kind of a much more efficient way compared with the random expectation strategy to improve the accuracy of the final machine learning model. And you can actually apply this idea to other applications, right? So for example, assuming you have a data set with some backdoor patterns, right? Also with a flicked label, right? So you could also try to understand whether we can find out those training examples with those backdoor patterns, right? So in this case, if you look at those training examples with small or often negative Shapley value, right? So they are actually often those examples that has the backdoor pattern and flipped labels, right? If you follow like the order of a Shapley value and try to inspect each of those labels, right? So this can also give you something that give you one strategy to improve the robustness of the machine learning pipeline, really kind of much faster than random strategy. And this can also be applied to fairness, right? So assuming you have a data set that's kind of unbalanced with some sensitive features, right? You have end-to-end machine learning pipeline, you try to measure the fairness as a matrix, right? If you look at those examples with a small Shapley value, so often those are the overrepresented examples. And if you remove them with that order, right, it can actually give you a strategy that can actually improve the fairness much faster than a random removal strategy. So all of these are kind of interesting application, in our opinion, about how to use Shapley value to improve the certain kind of metrics of the machine learning model. And because for the proxy pipeline, right, we can compute the Shapley value actually exactly in p time, right? So all of this is actually very fast, right? For reasonable size data set, we are talking about 100 milliseconds to compute all the Shapley value for all the input examples. So, and this can also be used, for example, for data cleaning, right? So let's say you have an input training set, and you have those uncertainties on those features, right? So, and then you have a cleaning oracle. You can ask a human to look at which cell to clean, and the human can actually give you the right answer of that cell. And you have kind of machine learning training pipeline, and you try to say, okay, so I can clean all those cells, but they are very expensive. How can we prioritize essentially which cell to clean, right? So in this case, right, if you clean those examples that minimize the expected entropy, right, which for the proxy pipeline we are able to compute in p time exactly, right? So you can actually have a very interesting kind of data cleaning mechanism for machine learning to really improve the final utility much faster than random cleaning strategy. If you think about why this is the case, right? So here's actually how we currently think about it, right? You can think about kind of like data noise in the training side as defining a whole bunch of possible world, right? So, and one of those possible world, right, corresponding to the real ground truth, right? So that is the 100% clean data set, but we don't know which one it is, right? So whenever you clean it, right, so you're actually going to eliminate a whole bunch of possible world that is actually not consistent with the true value, right? And you keep doing this, at some point, the entropy, right, is going to become to zero, right? In that case, it means that all the remaining noise don't really matter, right? So all those possible worlds have the same utility as the real clean data set. So if you take this view, right, so data cleaning really become entropy minimization, and you can actually, given the oracle to compute the entropy, you can actually apply a whole bunch of interesting results about sequential information maximization actually for this purpose. And another thing that we have been exploring is actually try to understand, once you understand essentially the value of data, you can actually use them to actually as mechanism to incentivize people to contribute the data in a data market, right? For example, think about data market where everyone contributes data and there's some consumer of those data to train a single machine learning model over those data, right? So one way to incentivize people to actually contribute high quality data is actually to attribute value back to them, right, fairly, right, to make sure that the high quality data providers also have essentially more kind of like get more benefit like out of this, right? So in this case, right, so if you can like use Shapley value, right, so for this, that's also give you a very natural way for to incentivize participations of users in the data market. And this actually is something that we have been doing, right? So there's actually two very small data market that we have been building, right? One is about try to help deforestation, right? So, and second is more on the healthcare side. So this is actually all we have today, right? Like really the things that we have been looking at over the last 2 years is really try to understand the impact of data to the final machine learning models. So one thing that we realized is that a better understanding of data can sometimes give you a better machine learning model, right? Which better can be in so many different ways, like better accuracy or fairness, so on and so forth. And essentially, I talk about the thing that we know at this moment. As you can see, it's pretty much all about that simple proxy model. It turns out we can compute this kind of different quantities in p time, but there are so many things that we actually don't know. But we deeply believe, right, making progress toward this line of work can actually give you kind of essentially more systematic support for the user to get models with better robustness, fairness, or accuracy. So that's all I have for today. Thank you for your attention. Right, so I think I'm right on time. So I'm happy to answer whatever question you have. Thank you.
Okay, yeah, thank you so for the very exciting talk. Let's see if we have questions. Please put in the chat or just unmute yourself. Yeah, and I think I will give you some time and I start with some of my questions. Actually, I have a lot of questions, but I will ask some like more high level, maybe hard to answer, but I think it would be an interesting discussion. So I wonder, for example, here in the Shapley value analysis you have, we actually focus on the data perspective, right? And of course, feature is important, we know, and we sometimes want to understand the importance or the contribution of the features. But I know we can do sharp during testing time. But in terms of the training time, like which feature is more important? Do you have some ideas or understanding about that? I think one challenge is that for data we can remove, but the model are still like that. But for feature, if we remove one feature, we have to retrain the model. Otherwise, we don't know what to assign to that dimension, right? So regarding these types of challenge, is there a better way to understand the feature importance? Yeah.
Yeah, so that's a very good question. So there are two things. The first one is thing I know. So essentially, I think from the logical perspective, right? If you think about whether Shapley value can still be used to measure feature importance, I don't see a reason why not, right? So actually, we have some preliminary results to show it's actually worked pretty well. And second is actually, can we still have efficient algorithm for that, right? So if you have a k-nearest neighbor or other type of models, whether you have still have a p-time algorithm, so that we don't know. Yeah, so we tried really hard, but we failed for a couple months. So maybe there's actually some, we need to kind of rethink about how to approximate, so like the Shapley value for features, right? So at this moment, so we know it works if you can compute it for many applications, but we actually don't know how to do that efficiently.
Yeah. I see. Yeah, I think there is a similar question in the chat, which is great. Yeah, I don't know whether that answers this question. The question asks whether these ideas apply to feature ranking and filtering as well. I think for filtering, it's possible, right? I mean, the pipelines in machine learning pipeline.
Yeah, so for filtering, it works. For ranking, that's a very good question, and I have no idea. Yeah, so for the ranking, I have no idea about ranking, but filtering should work. Yeah,
I see. Because filtering can also approximate by your KN tricks, right?
Yeah. Like filtering is more local compared with ranking. Yeah.
Mm-hmm. Okay. Yeah, maybe we have 1 minute. Let me know. Please put questions. I really want to ask another question. Maybe a lot of people here are also interested in. Is here to talk a lot about classifiers, right? We can use k-nearest neighbor, approximate, and but we also have other like model. For example, reinforcement learning. A lot of people care about it, and also there would be like data hungry problem. Like we always want sample efficiency for reinforcement learning. If we can clean up data, for example, we know which data are most useful. We don't need a lot of states. We only need a few states to train reinforcement learning. That will be great. So do you have some exploration or suggestions for like applying these types of techniques to reinforcement learning, types of like continuous pipelines?
Yeah, so I think, that's a good question. So for reinforcement learning, we don't know. But one thing that we have been doing is actually try to understand how to apply similar idea to essentially to language models, right? So there's a whole bunch of results about how k-nearest neighbor is actually a very powerful way to do question answering using language models, right? So there could be something that we can do to really debug those models. So that's something that we have been kind of exploring. For reinforcement learning, it's definitely very interesting, but at this moment, I have no idea how to do that.
See. Yeah, thank you very much.